Hi, I'm Chris Brown, and this is a lecture in a course on axiomatic design of manufacturing processes. This is section 2.1, and this introduces the second section of this course. So here are the expectations for starting this section of the course. One would be a qualitative understanding of axiomatic design. So this would include basic understandings of the axioms, which would, and lateral decompositions into domains, and top-down decompositions into increasing details, as well as construction and manipulation of the design matrix. The objectives for this intermediate axiomatic design section are to improve decomposition skills, increase the sophistication in applying axiom 1 in the design matrix, and address physical integration and coupling, relations between axioms 1 and axiom 2, innovation, and instituting axiomatic design in a company. For decomposition, it's essential to use axiomatic design software for problems with 5 or so FRs and DPs. The main impediment in using AD, axiomatic design in practice, is decomposition. People have trouble constructing good, useful decompositions. The decomposition is similar to force decomposition in a free body diagram. And dimensions, though, are user-defined, kind of like Lagrangian mechanics, and you need with a judicial choice of generalized coordinates. Some techniques for good decomposition. Remember, good decompositions need to be collectively exhaustive, mutually exclusive, and include just the minimum number of elements, usually functional requirements. It helps to have a theme for the decomposition, and we'll be covering that in this section. Also, there's decomposition by parts, like in calculus. That should be like in calculus. Also taxonomies and combinatorics. Design domains. Remember, first is the functional, and that can be mapped onto the physical domain as well as onto the process domain. For decomposition, we start at the top with FR0 and DP0. This decomposes into the next level, which might be 2 or more FR-DP pairs. And into the next level, here shown is a combination of 3 and 2 in the first and second branches, respectively. The design matrix. The design matrix is used to relate adjacent domains. When we say design matrix, we usually mean the functional and the physical domains, FRs and DPs, and we would call it the process matrix if it's relating DPs and PVs. The basis is in linear algebra, although we have only a limited case here because the design matrix should always be squared because the number of FRs should equal the number of DPs. It's best if it's uncoupled. It means it's a diagonal matrix. All the off-diagonal terms are 0. But we can make it work if it's decoupled, that is triangular. And then there's a specific order for adjusting the DPs in order to fulfill the FRs without having to iterate. So the design matrix can be represented like this, with the FRs down one side and the DPs across the top. And then the elements here are A1, 1, and so forth. And we can have any number, really, of FR and FRs and DPs, and so we can represent it with subscripts, so that AIJ can symbolize the influence of DPJ on FRI. So we could write it FRI is equal to AIJ, DPJ, and then AIJ might be represented as might be representing a coefficient or some other mathematical operation, like a table or a graph. If aij equals 0, then dpj does not influence fri. So the diagonal is best, and then we can have any order of adjustment. In this case, aij equals 0 unless I equals j. And so in this case, each dp influences only one fr. Now we have to have the diagonal non-zero or it won't work. Any order of adjustment works equally well in this case and then uncoupled. Now this is triangular, it's workable, it's decoupled, but there's only one order of adjustment, and that would be dp1, 2, 3, and so forth. So we can try to get A into a triangular matrix if it's not already there. So this is showing a triangular matrix, and this represents, in fact, 3 equations. And so that FR1 is only influenced, as we can see here, by DP1, which is symbolized by A11, and so forth. So for matrix manipulation, we move the DPs into columns and the FRs with the rows. And so this would also apply to the process matrix, of course. So moving the DPs with the columns looks like that. And then moving the FRs with the rows looks like this. So the steps in a decomposition would be first to identify the customer needs, develop an FR0 and a DP0, the highest level sort of design objectives consistent with the customer needs, develop the next level FRs consistent with the higher DPs, since we've already chosen a DP0, that puts constraints on this, and the customer needs. Then select the DPs and the corresponding to the FRs. Then check the developed FRs and selected DPs against axiom 1 and axiom 2 in the constraint. Modify and consider alternatives as necessary to ensure compliance with the axiom and the constraints. Go to the next level down or adjacent branch and start with 3 again. And then repeat until the solution is obvious. In other words, the decomposition is proceeded far enough so that no more detail is required for the design solution. So axiom 1 in the design matrix, it's assigning coupling for sort of when and how, inheriting coupling from the parent, from the child to the parent, kinds of coupling, coupling and manufacturing. And these are things that we'll cover in this section. So physical integration. We want things to be physically integrated as long as they can be functionally separate. And we can have a physical integration matrix, and we'll take a look at that. We'll also take a look at innovation opportunities by applying axioms 1 and 2. I apologize, I'm missing the 1. And recognizing potential for innovation, customer needs and FRs. And identifying new solutions. So different DPs, different PVs, and TRIZ can also be used. Knowledge management. How do we communicate the knowledge through utilizing the domains? In other words, we have some design knowledge that we've built up over time, or we can glean from the literature. So what's a good way to manage that knowledge? And we can design that system using axiomatic design, and we'll be talking about this. So this focuses on applying existing knowledge to adding value in the process of solving design problems. Instituting AD, axiomatic design, bringing it into a company. It may be good to start with some example projects. Often there's difficulties. Some people get stuck on the terminology. Many people are skeptical about a design method that makes these claims that it can sort out or identify the best solutions. And there's always this kind of corporate ladder problem and risk adversity in the corporate world. So people don't want to try something new that might fail. But I've never had a problem with axiomatic design failing. Manufacturing processes. So In the sections on manufacturing processes, we're going to be looking for commonalities in manufacturing process analysis, common FRs in mechanical components, some surface metrology, machining and chip formation, some on machine surfaces, some on energy partition in manufacturing and grinding, and some on additive manufacturing. So these will be covered in the sections on manufacturing processes. Thank you very much for your attention.